we're carrying on with this electrical worksheet, and the first question is, see if we can get in a little bit. There you go. Right. The teacher uses this circuit to investigate how the current in a circuit changes with temperature. So it's current with temperature. So if you look at this symbol here, it's like a resistor, but it's got this bent line through it, and it's called a thermistor. So remember, you've got your resistor, you've got a line through it, so that's your normal resistor. That is your fuse. What else do we need to know? Right, okay, so if you did a line and an arrow that way, or triangle that way, that is a diode. That is a filament lamp or bulb. What else do you need to know? Right, that there is a light dependent resistor, and you've got a light emitting diode, and it will have arrows pointing out. Do you need to know that? Let me check. No, I think I'm making that up. Stop making stuff up. Right. Right, what else do you need to know? You've got your right, okay, variable resistor is the main one that comes in. Right. So you've got, did I just do that? So let's put it up here. So you've got your resistor, and you've got a straight line across it with an arrow. That is a variable resistor. Right, done. So you've got the main ones. You know this, that's your voltmeter. It goes in parallel with the component. You normally just attach it to whatever component you need goes here. And then you've got an ammeter with an A, and you attach it so your component will go here. We said this is a switch, this is an open switch, and when they're touching, it's a closed switch. You've got a cell which is single, the plus and the minus, the long one's the plus. And if you've got more than one, what's that? If you got more than, really, if you have more than one, let me get that right, yeah. It is a battery, again plus there. Right, we said conventional current flows from plus to minus, but in the real world, which we don't need to know, it's going to flow that way, but we're not interested in that. Let's get that. Just remember, conventional current flows from plus to minus. Right, now we've done that. Right, the voltage across the battery, what the battery is pumping at, is 1.5, and it will be the voltage here. If I measured the voltage here and here, they've measured it for us. These two should add up to 1.5. So I can do 1.5 take away 0.91, and you should get 0.59 volts. Okay, so it's these two voltages, so V1 plus V2 equals V total. however you want to word it. State the formula linking voltage, current, and resistance. So we can write down, get into the habit of writing out the full worded one. V equals IR, current times resistance. V equals IR. Calculate the resistance of the thermistor. So we're going to look at this bit here, right? So what I'm going to do is get that color. So I know right, we've got to make sure we get this right in terms of the amount of working out. Let's move down. Let's move down a bit. What I'm going to do is I'm going to remove this. So I've got some room to play with. Right, let's go. Let's run with that. So we're looking at this question here. It's a 3 marker. So we know V equals IR. I know the voltage across here is 0.59 because I worked that out earlier in the earlier step. I know the current is that, so it'll be 6.2 times 10 to the minus 3. Remember we said milli is always 1000 or times 10 to the minus 3. Okay, whatever you're comfortable with. Times R. And then what you do is before you work that in your calculator, write it out as 0.59 divided by 6.2 times 10 to the minus 3. Right, I'm just writing this out, especially you don't have to write this out because some people are actually comfortable writing it like this. There you go. When you do that, you get the resistance is 95 ohms. Okay, let's move on. Describe the relationship between the temperature and the resistance of the thermistor. So this here, I was just looking at the book, and it is good to know this. Thermistor profile, resistance, temperature. So look, if they ask you to draw a temperature resistance profile for a thermistor, you know it's going to do that. No, it's going to behave like this, yeah. Right, describe the 2 marks. Describe the relationship between temperature and the resistance of the thermistor. So, right, okay. So we can say as, I always start off with this, as the temperature increases, the resistance increases. And then the second relation to say it is because it's not a, because can you see it's not a straight line, we can say it's a non-linear relationship. Yeah, it is a non-linear relationship. Physics is a bit weird, a bit strange, so you very precise. So you've got to bear that in mind. Explain how the reading of the voltmeter changes when the temperature of the room decreases. Explain how. So as the temperature increases, right, okay. So look, V equals IR. So the voltage is the same. So just say if that's 10 volts, that's going to remain the same. But as the resistance drops, so resistance just say was 10, so the current was 1. Now, along here, right, just say the resistance has dropped to 5, the current has increased to 2, yeah? So we can say the no, it's not working that way. No, my apologies. If I can't even get that. No. With the thermistor, let me get this right. Let's start this again. With the thermistor, the voltage decreases because the resistance of the thermistor increases. So the current in the circuit decreases, yeah? So we can say, so current in the circuit decreases. Yeah. I wasn't focusing on this word. That's the mistake I made. Right, so the voltage will decrease because the resistance has increased, so the current will decrease. Yeah, I worked it the other way. So what they're saying is you were here at just say 18 degrees, and when you went back and just say this is 10 degrees, the resistance was there. Now the resistance has gone up. If the resistance goes up, the current decreases because it was, yeah, I was going along the right lines. I should have carried on this thought. So the voltage will just say stay at 10 volts. The resistance has gone from just say, like we said, 10 ohms, so the current has to be 1 amp. Now in another scenario, because the temperatures dropped, the resistance has increased, so it's gone to 20 ohms. The voltage is still 10 volts. The battery is still knocking out 10 volts. So this must go to half an amp. So the current drops. And they've said the resistance has increased. Why? Because you've gone into a colder room. And just looking from that. Okay. Now without dilly-dallying too much on that, let's move on. Did we need to put this in? Is the next question. Right. Let's run with it anyway. A battery supplies a voltage of 12 volts and a current of that. So let me just get this right. V equals IR. V is 12 volts. Current is 0.25. We're trying to work out the resistance. Just say R equals 48 ohms. No, okay. A fan is switched on for 12 seconds, so that's T. And the fan gains 25 joules of energy. Calculate the efficiency of this energy transfer. Right, we know, where's the formula sheet? So we know energy transferred is VIT. Right, so that's how much energy's gone in. So the voltage is 12, the current is 0.25, and the time was 12 seconds. So if you worked out 12 times 0.25 times 12, you're going to get 36 joules. That's how much energy is being supplied. Now, according to this, the energy gained is, so the energy in and the energy out according to that is 25 joules. Right, so what we do is we do energy out divided by energy in times 100. Yeah. So what I'm going to do is just going to move that down and we'll write the formula down. So we have efficiency equals useful energy output over total energy over total energy output. So that becomes 25 over 36 times 100, and it works out as U right equals 69% or 70% or 69.4%. Okay. Yeah, okay, that's fair enough. Right, explain why the coil starts to rotate when there is current in the coil. So when you put current in the coil, it generates a magnetic field, and that's going to interact with the which way is that going? Clockwise. Yep. Right, just 1 second. Yep, it's the right hand grip rule. So there's the wire. I think it'll be easiest just to show you that one. Right. That's better. That'll make more sense. So it's the right hand grip rule, if you can call it that. So your thumb, so this is your wire. The current is going in that direction. You point your thumb there and you wrap your fingers around, and that's the way the field is going. So if the thumb is going in that direction and you wrap it, let me get that. So your fingers are going to wrap in that direction. So the magnetic field's going that way. So then what happens is that magnetic field and the magnetic field of the magnet, they cut, and then you're on your way. Right, so there's quite a few marks. according to the mass scheme, it's a 4 marker. So we know that the magnetic fields between the coil or the wire and magnet, permanent magnet, right, they cut each other into causing a resulting force on the coil, causing it to rotate. So what's happening is this way, it's turning this way. So the force just says up and the force here is down. That is causing it to move. That's it, 4 marker. Right, which side of the coil moves vertically upwards? Right, Y, Z, right, okay, let me get that the right way around. So you've got Y, let me get that, YZ is there, and XW is there. So it's saying which side of the coil moves vertically upwards? It's YZ. So that's going to move up, that's going to move down. It's based on Fleming's left-hand rule. Right, let me get that. Alright, this is what's going on. Alright, you've got your thumb going up, you've got your first finger, let's use another colour, you've got your first finger going across, and then you've got your second finger going in that direction. Right, so you've got, use red, and should we use this instead? Is that, yeah, okay, we'll have to use that. Right, okay, so those are your first things. So look, father, mother, child, right, is your force. What will M be? Movement? No, it's the other way. Right, I was just trying to recall what somebody told me. One of my students told me this. So it's mother, father, child. Mother for motion, father for field, and child for current. Right, okay, that's the way it was. I've just mother, father, child, mom and dad, mother, father, child. Okay, so looking at this, let's get rid of all this. It hurts my head this as much as it hurts your head. So now we know we've got the current there. That's the middle finger, right? We know we've got the current going in that direction. We've got, so that's the current, right? the field is, which is the field's running across so if yes, if the field is, no, the field's running that one. Let me get this right. The field is running that way. So if the field's running that way, the current's coming this way, the motion will be upwards. The motion or movement. Yeah, the motion of the movement will be upwards. That's why it goes vertically. Let me get rid of this. Oh, what's going on here? No, it's a disaster, that. No, it's not. Right, let's get rid of you. You there. That's fine. Right, it's a bit of a disaster this, but let's keep plugging away. So they said, which side of the coil moves vertically upwards? It's based on Fleming's left-hand rule. So take your left hand, put your middle finger facing which way the current's going. Your field lines are going that way. Look, we know what color can we get? Blue. We know the field lines always go that way, from north to south. Yeah. So we put our first finger that way, so the father, and this is the child. And then if you put your left hand that way, it's going to be a bit crazy, this, right? And then your thumb will point up. So that's why it's that one. Why is it? Did I just do the wrong one? YZ. Oh dear. Right, what we'll do is we'll come back to that sometime. Right, this is long enough. Call it quits there.